Swayam Prabha. Digital India. Educated India.
Okay. Okay. So now we have in the previous lectures I have shown some weight volume relationships, and their application. And I have very beginning I have mentioned that in the soil there are three important characteristics. They are permeability and compressibility and strength, and they are actually now we will try to start actually permeability and seepage. Before going to this permeability and seepage, how seepage means what, permeability means what? Actually, this permeability means water. Actually, when moved through water, that is permeability. So that means water movements, and water is very much present in the water. And what is the form of water present in the water, in the soil? What are the different types of water? Initially, I will just give some description, and then later on related to permeability, how to determine how the what are the parameters affect the permeability, and all those things. Slowly, one by one, we will discuss. So permeability and seepage. So the water in the different form actually available with the soil, and first thing I am defining actually subsurface water. Wall water found beneath the earth surface, that means below the earth ground level, whatever water present, that is actually subsurface water. And the main source of this water is actually nothing but rainfall, and that rainfall when drops in the soil, it will be percolates and fill the voids, and it penetrates downward, and this way water can penetrate actually theoretically up to 12,000 meters. And so that means we can expect water present up to that much depth, and below this level water cannot exist in free state, although water can be there in the form of chemical combination in the crystalline found in the chemical combination with the rock minerals. That means those water are not free water. So whatever water through rain and all weather change and evaporation, and then coming back, and water coming to the soil, and that soil percolating, so it can go theoretically up to 12,000 meters. Beyond that still water is there, but that water is not free water. This is in the form of minerals. And then subsurface can be split into two distinct zones. One is saturation zone. By the name itself, it is quite clear and obvious that saturation then means all soil mass will have a voids, and all void spaces will be filled up with water. This is the depth throughout which all the fissures, void spaces, etc., are filled with water under hydrostatic pressure. The upper level of this water is known as the water table, and or sometimes it is known as phreatic surface, sometimes also known as groundwater level. And water within this zone is called phreatic water or groundwater. So that means the water depth throughout which the all fissures, etc., that means from the downward direction water will be saturated, soil will be saturated. When you go upper direction, then it may not be saturated. The level at which up to which the saturated soil is there, that is actually limit, that is the upper level of this saturation zone, and that is called water table. Sometimes it is called phreatic surface, sometimes it is called groundwater level. And this water table not always a very level one, though in a smaller perspective. Actually, if I dig a hole here and see the level of water, and 3 meter or 5 meter away if I make a hole, you may get approximately same, but in the largest perspective, if you consider suppose here and 2 kilometer away, if I calculate or 100 kilometer away if I dig, then you may not get the water level same. So, that is what the water table tends to follow in a more gentle manner the topographical features of the surface. That means topographical features, the way topographical features are there, the actually parallel to that will be there. At groundwater level, the hydrostatic pressure is 0. That is important, that many times there will be brief short answer, multiple MCQ will be there, and that is the thing you have to remember, that in the groundwater level the hydrostatic pressure is 0. So, another definition of water table is the level to which water will eventually rise in an unlined borehole. That means, if I make a borehole, that means automatically, since it is a atmospheric pressure, so up to that water will come up. So, that is the indication that if I make a borehole, that water will come that level, and that is the actually water table. The water table is not constant, but rise and fall with variation of rainfall, atmospheric pressure, that means temperature, etc. Summer water table will go down, in the winter, in the rainy season it will goes up because of rainfall, like that. And coastal region again it will be varied because of the tide. When water table reaches the surface, springs like springs, lakes, swamps and similar features can be formed. So, water table sometimes comes to the surface also, because during flooding it can come to the surface. And permeability and seepage again next. So, this is the typically if the ground surface is like this, then your water level also will be parallel to this, but it is a very small distance, a few kilometer, a few meter within distance, you will see as a level. But when you use a long topography, if you consider, then you will get the water table also parallel to the generally ground surface. And then saturation zone I have divided, actually I wanted to divide in two parts. One I already explained, the saturation zone, another is aeration zone. This zone occurs between the water table and the surface, and again this can be split into three distinct zone section, and they are you can see capillary fringe. What is this? Owing to capillarity, water is drawn up above the water table into the interstices of the soil or rock. Actually, when the fine voids are there, through that, because of this capillarity action, what is the capillarity action, what other action will be there, that I will be coming to the next in the subsequent presentation. But here just I am briefly telling here that when the voids are very fine, then the sometime water will be drawn up above the water table, that is actually capillary fringe. Water held in this manner is in a state of suction or negative pressure, that I will show also theoretically, that is pressure is negative. Its height depends upon the material. Material means what? Whether it is silt, sand or clay. Again sand, whether it is fine or coarse. And in general, the finer the voids, the greater the capillary rise, and in silts the rise can be as high as 2.5 meters, and in clay it can reach twice that amount, which will be described later on. And then intermediate belt, that means capillary fringe means what? It was not below water table, above water table, but because of this capillary action, some water will be raised up and soil will be saturated. So, that is called capillary fringe. And intermediate belt is what? As rainwater percolates downward to the water table, a certain amount of water is held in the soil by the action of surface tension, capillarity, absorption, chemical action, etc. So, there are, because of so many action or so many properties present with this soil, this entire amount of water, whatever drops on the surface will not go to the or not join to the water table. So, some amount will be held. So, in the soil particles, so the water retained in this manner is termed the held water and is deep enough not to be affected by plants. Sometimes the plant sometime may not be able to reach that. So, some amount of water will be held in this. So, that is called intermediate belt. And then soil belt. So, this is actually topmost layer. This zone is constantly affected by evaporation and this will be spelling mistakes. It will plant transpiration. That means the top soil when it rains it will be moist, and when it will be sun there will be again evaporation, and because of that it will be dried. So, like that it will constant change of wet and drying condition. Most soil in contact with atmosphere either evaporates water or condense water into itself into its vapor pressure equal to atmospheric pressure, and soil water in atmospheric equilibrium is called hygroscopic water, while the moisture content is known as the hydroscopic water content. So, top soil whatever things are there, that is called soil belt, and from there roots of the plant will be in that zone and they will continuously taking water from this. So, this of course not really a soil mechanics issue, but to describe water present in water, what form, which area, which zone, what form. I just mentioned this aspect, but it is not really related to soil mechanics so far whatever we have mentioned, only other than water table and capillary rise, those things I will explain in elaborately later on. And this is actually this is the whatever things I have defined. They are actually number of things I have mentioned that you can see. These are actually internal water. This is the zone. This is the internal water in the chemical form, and from here to here actually this is actually saturation zone. This will be, and top of this will be water table, which I have defined. And then because of this capillary rise like this, if the fine particles water will be raised up, and then it will be saturated up to this. This is actually because of that, this is called capillary fringe. And then intermediate belt, that means this zone actually because of this absorption and all other properties, surface tension etc., some amount of when water drops here, it is going downward, but it is joining to water table, but still some parts water will be retained by the soil, that is intermediate water. And this is the soil water, that means on the within the soil some amount of water will be there, evaporation, transpiration, all those things are happening. So, these are all different zones what I have defined one by one. These are explained in this figure. This is aeration zone, this is saturation zone, and this is rock flow, that means water will be in the form of minerals. Now, this is the thing which is important for us, as I have told you that this is property of water, this is surface tension. Capillary is the effect of the surface tension. Capillary is the action and surface tension is the cause actually. Whatever I have said, that if the voids are fine and water will be raised, how it will be raised? Because of this capillarity, and capillarity caused by what? Surface tension. So, this is the thing, and let me define what is surface tension. Surface tension is the property of water that permits the surface molecules to carry a tensile force. Water molecules attract each other and within a mass of water, therefore balance out. So, each molecule will attract and so each other. So, within mass, so all are attracted by, so the inside mass it will be balanced, but in the surface, but at the surface however the molecules only attracted inwards and towards each other, which creates a surface tension, because one side only, the outside there is no molecules. So, because of that, surface tension causes the surface of a body of water to attempt to contract into a minimum area, and because of that a drop of water is spherical. And why it is so? Because of the surface tension effect, because periphery the one side tension is there, so it will be attract in a inward direction. So, because of that they will try to be in a spherical form. Surface tension is given the symbol T. Surface tension sometimes T, sometimes Ts, uniformly everywhere it is a surface tension symbol is T, and can be defined as the force in Newton per millimeter length. Newton per millimeter length that the water surface can carry. How much Newton per millimeter length it can carry, force can carry, that is actually your surface tension. The T varies slightly with temperature, but the variation is small, and average value usually taken for the surface tension of water as 0.00075 Newton per millimeter or 0.075 Newton per meter. So, this is the unit we have to remember. Sometime if it is not given surface tension, in some calculation it may be required. So, we should better to remember surface tension of water is 0.075, but it is mentioned that with temperature etc. it varies slightly, but average value is like this. So, one can use without any hesitation if there is a value not given. Then capillarity. The capillarity is in action. The fact that surface tension exists can be shown by the similar laboratory experiment in which an open-ended glass capillary tube is placed in a basin of water. And so, in a basin of water, if I put a very fine tube on the water, both sides open, subjected to atmospheric pressure, the rise of water within the tube is then observed. So, because of this you will see the some amount of, if I put a very thin tube within the water basin, you will see some amount of water will drawn up within the tube, and it is seen that the water weights the glass and the column of water within the tube reaches a definite height above the liquid in the basin. If it is like this, if I put a basin and water level is here, and if I put a capillary tube here, then you may find that water reached here. This is water level here, and then if this is a capillary tube, then you may find that water raised this much height. So, that is actually because of the capillary action. The surface of water forms a meniscus such that the curved surface of the liquid is at an angle alpha to the walls of the tube. Meniscus means actually when it is between the water and the surface of the glass, tension is there, so it is raised like this. So, meniscus typically will not be water level, never be, if it is a glass here, never be like this. It will be if the glass is like that, water level will be something like that. So, this angle, this tangent, that is alpha, this angle is telling this is with alpha angle walls of the tube. The base of the column is at the same level as this water in the basin. As the system is open, the pressure must be atmospheric. So, atmospheric here actually from the top it is atmospheric, and the basin there is atmospheric pressure. There are no externally applied forces that keep the column in position. To push the water, there is no external force is applied, but still water is rising, which shows that there must be a tensile force acting within the surface film of the water. So, that means there must be some tension which is drawing the water up. So, that is what we will try to see by some calculation also. You see, this is the one. This is the suppose tube which is exaggerated, is actually enlarged view only you can imagine, and then this is the meniscus, and this angle, this is the surface tension direction is this with alpha, and diameter d suppose, and if the surface tension inclined to this, then you can take a component in this direction, component in this direction, and then finally I can consider the equilibrium. The equilibrium actually what? In the periphery of the glass tube, the tensile force is there, that will be into multiplied by your perimeter, and then atmospheric pressure is there, and this side is atmospheric, then bottom there must be some pressure which is lifting this. So, that pressure multiplied by the cross sectional area, though it is spherical, the area will be different, but since it is small, we can approximately take this as a circular area, the cross section of the tube, and if you take that way, then we can find out how much height it can rise if you diameter is given. And you can see this water table is here, and if that means here it is already mentioned is atmospheric, and that means if I go this direction, then water pressure, hydrostatic pressure will be gamma W times H going downward, but when it is going above, then it is negative. So, that is what it is going up, it will be minus. When above water table, it is against gravity, so that will be minus. So, that with keeping these points in mind, and we can see that different calculation. So, Hc is the height of water column, R is the radius of the tube, gamma W is the unit weight of water. Consider the force equilibrium in vertical direction. You can see we have taken 2 pi r is the perimeter, 2 pi r is the perimeter, 2 pi r is the perimeter T cos alpha we have taken, that is force surface tension force in the particular direction component we have taken. This is one force, and upward direction, and from bottom also there is a U pressure, we assume that pressure into pi r square. So, these two in the same direction. So, since there is no external force applied, so summation of these two force will be 0. So, that is what we have done. Then you can see ultimately you are getting the U value, the negative sign, and the value is 2 T cos alpha by r. And U, since actually the height and it is above water table, that definitely minus Hc. So, gamma W Hc is the U, and if you substitute that, then you will get the value hence, as expected, we see that U is negative. That is what we have shown in the water within the column is in the state of suction, that means since it is negative, the maximum value of this negative pressure is and occurs at the top of the column, and an expression for height Hc can be obtained by substituting in the above expression. You can see that when Hc equal to, so this is the expression we can get, and you can see the rise will be inversely proportional to radius. So, finer the particles or the voids, then your rise will be more. So, that is what it is clear from this. So, because of that, in the clay soil, the capillary rise will be maximum, silt will be in between, and in the sand and gravel will be difficult, but sand also can rise up to some height. From the above two equation, we see that the magnitude of both U and Hc increases as R decreases. What I said, inversely proportion. With the use of expression for Hc, we can obtain an estimate of the theoretical capillary rise that will occur in a clay deposit. So, clay size we have mentioned already in the classification, that is less than 0.002 millimeter. So, average void size if in a clay, if I consider 3 micrometer and taking alpha equal to 0, what in the expression alpha is there for water to soil, you can take alpha equal to 0, and if you take this size as a 3 micrometer, the formula gives you H equal to 5 meter. That means, in a clay soil, if I take the average side void side, then we can the capillary rise can be at as high as 5 meter. However, capillary rise of this magnitude seldom occur in practice, as the upward velocity of water flow through a clay in capillary fringe is extremely small and often restricted by absorbed water films, which considerably reduces the free diameter of voids. So, that whatever theoretical diameter we have considered, that much diameter may not be available because of this water present in it, and also this resistance. There are different types of resistance will be there, though theoretically if you see, but much lower than that value it can reach. Okay, thank you.